All right, let's talk about one of the biggest single challenges standing between us and the full power of quantum computing. We're talking about the constant, nagging problem of errors. First things first, let's just remember what's at stake here. The promise of quantum computing is, and I'm not exaggerating, almost beyond imagination. We're talking about machines that could discover new medicines, design revolutionary new materials, and crack codes that are basically unbreakable today. Which, brings us to the big question. If these things are so potent, why aren't they already changing the world? Well, the answer comes down to one little word: noise. Okay, so here's how we're going to break this down. First, we'll get into the fundamental problem itself. Then we'll explore the really clever solutions scientists came up with. We'll see how it actually works, step by step. Then we'll face the massive hurdles we still need to clear. And finally, we'll look ahead to the fault-tolerant future that all of this could make possible. So let's jump right in with the quantum conundrum. At the very heart of every quantum computer, there's this deep, kind of frustrating paradox. They are incredibly powerful, but at the same time, they are unbelievably fragile. So with the qubits, the quantum bits that do all the work, exist in these really delicate states of superposition and entanglement. The best way to think of them is like super sensitive soap bubbles. The tiniest little thing from the outside world, a stray magnetic field, a tiny shift in temperature, can pop them. And when that happens, a process called decoherence, the precious quantum information they were holding just vanishes. And this is where things get really tricky. In your phone or your laptop, an error is usually pretty simple. It's a bit flip. A 0 accidentally becomes a 1. Easy enough. But a qubit, it's a whole different beast. Sure, it can have a bit flip, but it can also suffer something called a phase flip. Imagine the qubit is like a tiny spinning compass. A bit flip is like knocking it from pointing north to pointing south. A phase flip is more like reversing the direction it's spinning. And, this is the really crucial part, it can get hit with both errors at the exact same time, which makes fixing the problem way, way harder. And get this, the threats are coming from everywhere. It's a constant assault. The very operations you use to make a calculation can be imperfect. Qubits can accidentally interfere with their neighbors. That's called crosstalk. And the outside world is basically a constant enemy. You've got heat, vibrations, even cosmic rays from deep space can fly in and knock a qubit off course. So, with this constant storm of errors, how on earth do you fight back? Well, the solution is as ingenious as it is, honestly, a little counterintuitive. The answer is a whole field of study called quantum error correction, or QEC for short. The idea isn't to build a perfect qubit that never makes a mistake. That might actually be impossible. Instead, the goal is to build a smart system that can catch and fix errors on the fly. But here's the kicker. For a long time, everybody thought this was impossible. See, in classical computers, you often just make copies of your data as a backup. But there's this fundamental law in quantum mechanics called the no-cloning theorem that says you simply can't make a perfect copy of an unknown quantum state. It looked like a total dead end. But then, back in 1995, a physicist named Peter Shor had this genius idea. He realized you don't need to copy the information, you just need to spread it out. Instead of putting all your eggs in one very fragile basket, you share the information across a whole bunch of them. And this is the absolute key idea. We create a single, super robust, logical qubit by encoding its information across a whole team of less reliable physical qubits. That way, if one of those physical qubits messes up, the rest of the team holds enough information to see the error, figure out what it was, and fix it. The logical information stays safe. Okay, so how does this actually work in practice? This isn't just a one-time setup. It's an active, continuous cycle of defense that has to run for the entire computation. It all happens in 3 steps. First, you encode your important logical information across that team of physical qubits. Second, you bring in these special helper qubits, they're called ancilla qubits, to check up on the team. Now, they don't look at the data itself, that would collapse the quantum state. They just check for disagreements among the qubits. This reveals what's called an error syndrome, which is basically a fingerprint of the specific error that happened. Third, that syndrome, that fingerprint, gets fed to a classical computer which acts like the brain of the operation. It figures out what went wrong and where, and then zaps the system with just the right pulse to correct it. And I really want to stress this. This cycle has to run over and over and over again. We're talking thousands, maybe even millions of times a second. It's a vigilant defense system that's running constantly, right alongside the main calculation. So if you're thinking, wow, that sounds incredibly difficult to pull off, you are 100% right. This is one of the most demanding engineering challenges in all of science today. To give you an idea of this scale we're talking about, to run the really powerful algorithms, the game-changing stuff, scientists figure we need the error rate for our logical qubits to be less than 1 in 10 billion operations. I mean, just think about that. That's a level of accuracy that is almost unbelievable, and it's way beyond what any single physical qubit can do on its own. And the roadblocks are just massive. First off, there's the resource overhead. You might need 1,000 or even more physical qubits just to create one single high-quality logical qubit. Then there's decoder speed. That classical brain has to be mind-bogglingly fast to find and fix errors before new ones pop up. And on top of all that, there's scalability. Just being able to manufacture millions of near-identical qubits is a monumental challenge all by itself. Okay, so with such a massive mountain to climb, what's the end game? What does success actually look like? The goal, the holy grail of all this, is true fault-tolerant quantum computing. A machine that is so robust it can correct errors faster than they build up. That would allow it to run any calculation, no matter how long or complex, without getting derailed by noise. And let's be clear, right now, quantum error correction is the only path we know of to build a machine like that. It's not just an important piece of the puzzle. Most researchers will tell you it is the absolute cornerstone of the entire field. This is the technology that's going to bridge the gap. It's what will let us move beyond what we call the NISQ era. That's NISQ, and it stands for Noisy Intermediate Scale Quantum, which is just a fancy way of saying the experimental devices we have today are small and really, really error-prone. QEC is the key to building the powerful, reliable machines of tomorrow that can actually solve those world-changing problems. So the path forward is clear, but man, is it steep. Solving these challenges of overhead and speed and scale is a grand quest for a whole generation of scientists and engineers. And really, their success is going to determine how quickly we get to unlock the next great age of computation.